Welcome to Navakokon Education Society's DBJ College, Chiplun. The online session conducted by Shriram Dandekar. My phone number and WhatsApp number is 94200 You can ask your doubts on the same. We are studying Mathematics Part 2, where we are studying applications of the derivatives. And in this topic, applications of derivatives to tangents and normal we have seen, derivative as rate measure we have seen, we also have seen the approximations. Today we are going to study the Rolle's theorem and Lagrange's mean value theorem. Rolle's theorem, the statement is, if f is a real valued function that satisfies the following three conditions. First condition, f is defined and continuous on the closed interval ab. F is differentiable on the open interval ab. And third, fa is equal to fb. Then there exists at least one point c in the open interval AB such that f dash c is equal to 0. The statement is here, but we will see this using a diagram. The first point, f is defined and continuous on closed interval AB. That means for x equal to a and for x equal to b, you can draw the function from this point a to this point b continuously without any break. Second condition, it is differentiable on the open interval ab. That means there should not be any corners like this. Any corner or continuous means there is no break, because the existence of tangent depend on the continuity and differentiability. Only in these two cases the tangent exists, and therefore for the existence of tangent we should have these two conditions. Third condition, fa is equal to fb. That means this for a and b the value of function y must be same. Now the statement says that there exists at least one point c for which f dash c is equal to 0. Please recall that f dash c means the slope of tangent at point c. So at point c, for the function, to the graph of the function, draw a tangent, and this tangent is horizontal, therefore its slope f dash c is equal to 0. This is the statement of Rolle's theorem. Let us see this in few different words. If the object is in the same place at two different instants, say t equal to a and t equal to b, then fa is equal to fb, satisfying the hypothesis of Rolle's theorem. Two different moments, the object is at the same place. Therefore, the theorem says that there is some instant of time t equal to c between a and b where f dash c is equal to 0. Again, please recall that f dash is nothing but derivative of displacement, which is equal to velocity, and therefore when object is at the same place at two different instants, in that case you should have velocity equal to 0 at some point in between. The Rolle's theorem applied to theory of equations. If a and b are two roots of a polynomial equation fx equal to 0, then Rolle's theorem says that there is at least one root c between a and b for f dash x is equal to 0. That means if a and b are two roots of a function polynomial equation, then f dash x must have one root between a and b. This is what this theorem says. Next implication from Rolle's theorem is, the Rolle's theorem implies that a smooth curve cannot intersect horizontal line twice without having horizontal tangent in between. I will show you here with diagram. Suppose fa and fb, two are equal things. The y values are same for these 2 points. Now this is the horizontal line. If I draw a continuous curve over here like this or like this, any curve will do. This curve once cuts this horizontal line at point this P, end point at this end point Q. So this Rolle's theorem implies that smooth curve cannot intersect horizontal line twice without having horizontal line in between. The simplest way is the previous curve, the simple one C. Now here cuts once, cuts twice. One horizontal line or one horizontal tangent is possible over here. Now in this case, one horizontal tangent here and other here. So two tangents are possible. The curve, the statement says at least one. So there can be more than one. Here you will observe more than one horizontal tangents are available. Now the converse of Rolle's theorem is not true. That means if a function f satisfies that f dash c is equal to 0 for some c belonging to a and b, then this doesn't mean that the hypothesis should hold. Fa should not be equal to fb, or f may not be continuous, or f may not be differentiable. The converse of Rolle's theorem is not true. Let us see some problems. Verify Rolle's theorem for the following. Fx is equal to x cube minus 3x plus 3, a equal to 0 and b equal to 1. Now here fx is this, it is a polynomial function and therefore it is continuous everywhere, therefore it is continuous on closed interval 0 to 1. Also the derivative f dash x is equal to 3x square minus 3 exists for all values between 0 and 1. Therefore this function is differentiable in open interval 0 1. Now let us find f of 0. Put x is equal to 0 here. 0 cube minus 3 into 0 plus 3, f of 0 becomes 3. And f of 1, put x is equal to 1. 1 cube minus 3 into 1 plus 3, it is 1. So f of a is 3 and f of b is 1. fa is not equal to fb. Therefore the condition for Rolle's theorem is not satisfied, and therefore Rolle's theorem cannot be applied for this polynomial for this domain. The second problem, fx is equal to tan x, x between 0 and pi, that is a equal to 0 and b equal to pi. We know that tan x is not defined at x is equal to pi by 2. X equal to pi by 2, the tan function is not defined, hence it is not continuous at x equal to pi by 2. Therefore the function fx is equal to tan x is not continuous in this 0 to pi, and therefore Rolle's theorem is not applicable for this tan x between 0 to pi also. Third problem, fx is equal to mod x. Again we know that mod x is the function which is continuous everywhere from minus infinity to plus infinity. Therefore it is continuous from minus 1 to plus 1. But we have studied that this function mod x is not differentiable in minus 1 to plus 1, that is at x equal to 0, because we know that graph of the function is something like this. Mod x, the graph is like this. There is a sharp corner at x equal to 0, and therefore at this x equal to 0 the function is not differentiable, and since the function not differentiable, the Rolle's theorem cannot be applied here as well. Let us see some instance where the Rolle's theorem is applicable. Firstly, we will take simple problem. Check whether the conditions of Rolle's theorems are satisfied by the following function. Fx is equal to 2x cube minus 5x square plus 3x plus 2, x belonging to closed interval 0 to 3 by 2. This is problem from book. Let us solve this. Fx is a polynomial function. Polynomial functions are continuous everywhere, therefore it is continuous for the given domain. Polynomial functions are differentiable everywhere, therefore it is differentiable for the open interval 0 to 3 by 2. Now a equal to 0, the first point of the interval, and b is equal to 3 by 2, the second point of the interval. Now for x equal to a, that is 0, we get f of a. Put here x is equal to 0, and we have the value fa equal to 2. Now for x is equal to b equal to 3 by 2, in this fx put x is equal to 3 by 2. 2 into 3 by 2 cube minus 5 into 3 by 2 square plus 3 into 3 by 2 plus 2, which is equal to 2. Now we have found out the value of fa and fb. fb is equal to 2. I have repeated the step, and therefore fa is equal to fb equal to 2, and therefore the Rolle's theorem is applicable for this function. The conditions for Rolle's theorems are satisfied, and in the question we want only that. Check whether the conditions of Rolle's theorem are satisfied or not. We are not going to verify the Rolle's theorem in this particular problem. Please remember this. Let us take the next problem. Verify Rolle's theorem for the function fx is equal to x into x minus 1 bracket square in the interval 0 to 1. We have fx is equal to, this square is x square minus 2x plus 1 multiplied by x, and we will get fx is equal to x cube minus 2x square plus x. We observe that fx being polynomial function, it is continuous on closed interval 0 1. f dash x is equal to 3x square minus 4x plus 1, which clearly exists for all values of x belonging to closed interval 0 1. Hence it is for open interval 0 1 as well, and therefore both the conditions are satisfied. Let us see the third condition. One must notable thing over here, the notation used here for open interval is this, the reverse rectangular brackets. This is one of the notation for open interval. Fx is differentiable on open interval 0 to 1. f0 equal to 0, put it 0 here, and f1 is also 0, putting x equal to 1 we get 0. So f0 equal to f1, that is a equal to b. The condition for Rolle's theorem is satisfied, and therefore Rolle's theorem is applicable. There must be some c belonging to open interval 0 1 such that f dash c is equal to 0. This part is behind me. Therefore f dash c equal to 0 implies 3c square minus 4c plus 1 equal to 0. Why is this so? The reason behind that, observe f dash x over here. F dash x is 3x square minus 4x plus 1. So f dash c is equal to 3c square minus 4c plus 1, and therefore f dash c equal to 0 gives us 3c square minus 4c plus 1 equal to 0. Solving this quadratic equation by factorization method, we get c equal to 1 or c equal to 1 by 3. The basic interval given to us is closed interval 0 to 1. This is the interval given to us. This c equal to 1 does not belong to this interval, but c equal to 1 by 3 belongs to this interval. 1 by 3 belongs to open interval 0 1, and therefore Rolle's theorem is verified. C equal to 1/3 belongs to open interval 0 1 such that f dash c equal to 0. We have found out this c, and in this way the Rolle's theorem is verified. Let us take the next problem. Verify Rolle's theorem for the function fx is equal to log of x square plus 2 minus log 3 on closed interval -1 plus 1. Let us solve this. Clearly fx is equal to log of x square plus 2 minus log 3 has a unique and definite value for each x belonging to closed interval -1 to +1. Every x has a value and that value is unique. Observe that if I put x is equal to 1, I will get 1 square is 1 minus 1 square is 1 plus 2 3, log 3 minus 3 is 0. X is equal to -1 as well as x is equal to +1, I am getting the same value. Value unique means for every x there is unique value. For single value of x there is no two values of y. In that case it would not be a function. So this is a continuous function. So at every point of closed interval -1 plus 1, the limit of the function equals to value of the function, which tells us the function is continuous on closed interval 0 1. F dash x, use the chain rule, log bracket derivative is 1 upon bracket into derivative of bracket. So it is 2x upon x square plus 2 f dash x, which clearly finite for each value of x between -1 and +1, and therefore f dash x also exists for all values between in the open interval -1 +1. Now as we have seen, f of -1 is equal to f of 1 is equal to 0. So condition number 1, continuous, satisfied. Condition number 2, differentiable, satisfied. And condition number 3, fa is equal to fb, satisfied. And therefore Rolle's theorem is applicable over here. All conditions of Rolle's theorem are satisfied, hence Rolle's theorem is applicable. Let us apply it. There must exist some point C in open interval -1 +1 such that f dash C is equal to 0. F dash C equal to 0 means 2c upon c square plus 2 equal to 0. Now 2c upon c square plus 2, it comes because of this. F dash x is equal to 2x upon x square plus 2. Therefore f dash c is equal to 2c upon c square plus 2. So 2c upon c square plus 2 equal to 0 implies that 2c equal to 0. Therefore c equal to 0. This c equal to 0 lies between -1 and +1, and therefore Rolle's theorem is verified. Thus c equal to 0 between open interval -1 +1 such that f dash c equal to 0, and hence Rolle's theorem is verified. Let us see the upgraded version of the same theorem. It is called as Lagrange's mean value theorem. The mathematician Lagrange has given this theorem. This statement of this theorem is: let f is real valued function such that fx is continuous on closed interval ab, fx is differentiable on open interval ab, then there exists a number c in the open interval ab such that f dash c is equal to fb minus fa upon b minus a. It is exactly similar to the Rolle's theorem, only the third condition is not here. And f dash, instead of f dash c equal to 0, here f dash c is equal to fb minus fa upon b minus a. Let us see why is it so. Let us draw a diagram. The diagram drawn over here, x-axis is at this point, x-axis over here, y-axis here, and a continuous and differentiable function, its graph is plotted here. Now points A and B are there. Corresponding to point A, there is a point on x-axis, small a. Corresponding to point B, there is a point on x-axis, small b. It is here and we cannot see that due to my face. It is hiding behind that. Now consider this chord AB. Observe here, if the function is continuous, then we must find a tangent which is parallel to the chord. Tangent parallel to the chord. What is slope of this chord? y2 minus y1 upon x2 minus x1. This point B is B comma FB. B comma FB is this point. And similarly, this point is A comma FA. y2 minus y1 upon x2 minus x1, fb minus fa upon b minus a is the slope of this chord. The tangent is parallel to this chord, therefore slope of tangent at point C, f dash C, is equal to fb minus fa upon b minus a. In words, Lagrange's mean value theorem states that for any real valued differentiable function which is continuous at the two endpoints, there is at least one point at which the tangent is parallel to the secant through its endpoints. This is what Lagrange's mean value theorem. Please observe that if this fb is equal to fa, then we get 0 here, and fb equal to fa is the third condition in Rolle's theorem. Therefore, this Lagrange's mean value theorem is equal to Rolle's theorem when fb is equal to fa. Let us solve problems. Verify Lagrange's mean value theorem for the function fx is equal to x into 2 minus x in the closed interval 0, 1. Given function is x into 2 minus x, that is 2x minus x square. It is a polynomial, so continuous. It is polynomial, therefore differentiable and derivative exists. So first both the conditions are satisfied. Therefore both the conditions of Lagrange's mean value theorem are satisfied. Now there must exist C between 0 and 1 such that f dash C is equal to fb minus fa upon b minus a, f1 minus f0 upon 1 minus 0. Put x is equal to 1 here, you will get 2 into 1 minus 1 square, it is 1. And put x is equal to 0 here, you will get 0. So f of 0 is 0, f of 1 is 1, 1 minus 0 is 1. So f dash C is equal to 1. But f dash x is 2 minus 2x. So f dash C is 2 minus 2c. And therefore 2 minus 2c, 2 minus 2c is equal to 1. And therefore C is equal to half. By solving this, C is equal to half, which belongs to open interval 0, 1. And therefore C equal to half belonging to open interval 0, 1 such that f dash C, that is f dash half, is equal to f1 minus f0 upon 1 minus 0 exist, and therefore Lagrange's mean value theorem is verified for this function. Let us solve one more problem on Lagrange's mean value theorem. Fx is equal to x minus 2 upon x plus 2. Find all values of C such that the mean value theorem for the function is satisfied. The interval is given closed interval minus 1, 2. Fx is x minus 2 upon x plus 2. We know that this function is not defined when denominator is equal to 0. Therefore this function has a discontinuity at x equal to minus 2, that is when the denominator equal to 0. But we need not worry about that, because this minus 2 does not belongs to the given closed interval minus 1, 2, and therefore the function is continuous in closed interval minus 1, 2. Also it is a rational function, therefore its derivative exists, and therefore it is differentiable on open interval minus 1, 2. Hence LMVT or mean value theorem is applicable to this function on the given interval. F of minus 1. First of all, let us find FA and FB. f of minus 1, put x is equal to minus 1, get minus 3. F of b, put x is equal to 2 and get 2 minus 2, that is equal to 0. We have 0 here. Now let us find f dash x. Find derivative of x minus 2 upon x plus 2. Certainly you can find this derivative by using u upon v rule, but instead of that I like to use this way, add and subtract 2. So it is numerator is x plus 2 minus 4 upon x plus 2. It is 1 minus 4 upon x plus 2. Its derivative finding is very easy job. 1 derivative 0, minus 4 as it is. Derivative of 1 upon x plus 2 is minus 1 upon x plus 2 square. Minus 1 into minus 4, it becomes 4, and f dash x is 4 upon x plus 2 bracket square. F dash c is equal to fb minus fa upon b minus a gives us 4 upon c plus 2 bracket square is equal to 0 minus minus 3 upon 2 minus minus 1. We have applied the mean value theorem here. Four upon c plus 2 bracket square is equal to 3 by 3 is equal to 1. Therefore c plus 2 bracket square is equal to 4. Therefore opening this bracket, c square plus 4c plus 4, cancelling 4 on both sides, we get c square plus 4c equal to 0. That means c equal to 0 or c is equal to minus 4. We have two values for c equal to 0 or minus 4. Out of these two values, c equal to 0 lies in the open interval minus 1, 2, and therefore the mean value theorem is verified. Now it is your job to solve more and more problems on this Rolle's theorem and Lagrange's mean value theorem from the textbook exercise, and ask me your doubts if any. Thank you very much for this session.